Welcome to Fact Pulse, where we delve into the many wonders of the universe. Please like and comment on this video and give us a follow so you don't miss any of our other great content. Imagine traveling to a distant galaxy. Picture yourself embarking on a journey to a place so far away that it seems almost unreachable with our current technology. The vastness of space is both awe-inspiring and daunting. The distances between stars and galaxies are so immense that even the fastest spacecraft we can conceive would take thousands, if not millions of years to reach them. What if you didn't need a spaceship that takes millions of years? What if there was a way to bypass the conventional limitations of space travel? Imagine a scenario where you could leap across the cosmos in the blink of an eye, reaching distant galaxies without the need for a spaceship that would take an eternity to get there. What if you could take a shortcut? A direct path through the universe that defies the traditional rules of physics as we know them. This is where the concept of wormholes comes into play. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. That's the enticing idea behind wormholes. They are like tunnels through the fabric of space-time, potentially connecting distant points in the universe in a way that allows for instantaneous travel. The very thought of such a phenomenon is enough to capture the imagination of anyone who has ever looked up at the night sky and wondered what lies beyond. They are like tunnels through the fabric of space-time. Wormholes capture our imaginations. Could they really exist? The idea of wormholes is not just a flight of fancy, it has its roots in the complex and fascinating world of theoretical physics. Scientists have been exploring the possibility of wormholes for decades, trying to understand if they could be more than just a mathematical curiosity. Let's explore the science behind these cosmic shortcuts. The concept of wormholes was first proposed by Albert Einstein and Nathan Rosen in 1935, as part of their work on the theory of general relativity. They described these hypothetical structures as bridges through space-time, which could potentially connect distant regions of the universe. We often see wormholes in science fiction. These imaginative depictions fuel our curiosity and make us wonder about the possibilities. Science fiction has a way of taking theoretical concepts and bringing them to life in ways that are both entertaining and thought-provoking. Think of movies like Interstellar or Stargate. These films show us traveling vast distances in an instant. It's a thrilling concept. In Interstellar, for example, the characters use a wormhole to travel to another galaxy in search of a new home for humanity. Stargate, on the other hand, features a network of wormholes that allow for instantaneous travel between different planets. These films show us traveling vast distances in an instant. It's a thrilling concept. The idea of being able to traverse the universe so quickly is not only exciting but also opens up a realm of possibilities for exploration and discovery that we can only dream of with our current technology. But is it just fantasy, or could wormholes actually be real? The question of whether wormholes could exist in reality is one that scientists are still trying to answer. While the mathematics of general relativity allows for the possibility of wormholes, there are many challenges and unknowns that need to be addressed before we can determine if they could actually be created or used for travel. To understand wormholes, we need to delve into the mind-bending world of Einstein's theories. Einstein's theory of general relativity revolutionized our understanding of gravity and the nature of space-time. It provides the framework for understanding how wormholes might work, but also presents significant challenges that must be overcome if we are ever to make these cosmic shortcuts a reality. So, what exactly is a wormhole? This question has fascinated scientists and science fiction enthusiasts alike for decades. A wormhole, in essence, is a theoretical passage through space-time that could create shortcuts for long journeys across the universe. Picture a piece of paper. This simple analogy helps us understand a complex concept. Now imagine folding that paper in half. By doing this, we bring 2 points on the paper closer together. The paper represents space-time, the fabric of our universe. Space-time is a 4-dimensional continuum that fuses the 3 dimensions of space with the dimension of time. A wormhole is like a hole punched through the folded paper. This hole acts as a bridge, connecting 2 separate points in space-time. It connects 2 distant points. Instead of traveling the long way across the paper's surface, you could instantly travel through the wormhole. Imagine the vast distances in space. Traveling from one star to another could take thousands of years with conventional technology. But with a wormhole, this journey could be instantaneous. This is the basic idea behind wormhole travel. It's a concept that has been explored in countless science fiction stories, from Star Trek to Interstellar. It's a shortcut through the vastness of space. But while the idea is tantalizing, the reality is much more complex. But how do these theoretical tunnels form, and are they stable enough for travel? That's where Einstein's theory of general relativity comes in. According to this theory, massive objects can warp space-time, creating the potential for these shortcuts. However, the existence of wormholes remains purely theoretical, as we have yet to find any physical evidence of them in our universe. Albert Einstein revolutionized our understanding of gravity. Before Einstein, gravity was simply thought of as a force that pulled objects towards each other, as described by Isaac Newton. Newton's laws explained how gravity worked, but not why it worked that way. Einstein, however, took a different approach. He proposed that gravity is not just a force, but a consequence of the curvature of space-time itself. This groundbreaking idea was part of his general theory of relativity, published in 1915. He showed us that gravity is not just a force. Instead, it is a geometric property of space and time, or space-time. This was a radical departure from the Newtonian view and required a new way of thinking about the universe. According to Einstein, massive objects like stars and planets cause space-time to curve around them, and this curvature affects the motion of other objects. It's a curvature in space-time. Imagine space-time as a flexible four-dimensional fabric. When a massive object, such as a planet or a star, is placed on this fabric, it causes a dent or a curve. This curvature is what we perceive as gravity. Smaller objects move along the curves in this fabric, which is why they orbit larger objects. Imagine a bowling ball placed on a trampoline. The trampoline represents the fabric of space-time, and the bowling ball represents a massive object like a planet. The ball creates a dip in the trampoline's surface. This dip is analogous to the curvature of space-time caused by the presence of a massive object. The more massive the object, the deeper the dip. That dip represents the curvature of space-time caused by massive objects. This curvature affects the paths of other objects moving nearby, causing them to follow curved trajectories. Now imagine rolling a marble across the trampoline. The marble represents a smaller object like a satellite or a planet moving through space-time. The marble's path will curve as it passes the bowling ball. This is because the marble is following the curved shape of the trampoline, just as objects in space follow the curved shape of space-time. This is similar to how light bends around massive objects in space. When light passes near a massive object, its path is bent due to the curvature of space-time. This phenomenon is known as gravitational lensing and has been observed in many astronomical events. Einstein's theory suggests that if space-time can curve, it might also be able to fold and connect distant points, forming a wormhole. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. While we have yet to find concrete evidence of wormholes, the idea continues to captivate scientists and science fiction enthusiasts alike. Einstein's insights into the nature of gravity have opened up a universe of possibilities, forever changing our understanding of the cosmos. While Einstein's equations allow for the possibility of wormholes, there are major challenges. One of the biggest hurdles is the need for exotic matter. This hypothetical matter would have negative mass and energy. We've never observed exotic matter. It exists only in theory. Even if we could find or create it, there's another problem: stability. Wormholes are thought to be incredibly unstable. They might collapse instantly upon forming. This instability poses a significant challenge for anyone hoping to use wormholes for interstellar travel. Section 5. Chasing wormholes, from equations to experiments. Despite the challenges, scientists are fascinated by wormholes. They continue to explore these theoretical objects through mathematical models and simulations. Some researchers believe that microscopic wormholes might exist at the quantum level. Facilities like the Large Hadron Collider are searching for evidence of these tiny wormholes. While we haven't found any yet, the search itself pushes the boundaries of our understanding of the universe. Section 6. Wormholes on the silver screen, fact or fiction. Wormholes have become a staple of science fiction, often used as a plot device for faster-than-light travel. Movies like Interstellar depict stunning visuals of wormholes connecting different parts of the universe. While visually captivating, these depictions often take liberties with scientific accuracy. The stability issue, the need for exotic matter, and the sheer energy requirements of creating a traversable wormhole are usually glossed over for the sake of storytelling. Section 7. The Uncharted Territories of Space and Time. The concept of wormholes remains firmly in the realm of theoretical physics. However, the pursuit of understanding these cosmic shortcuts deepens our knowledge of the universe. The challenges are enormous, but so is the potential payoff. Imagine a future where we could traverse the vast cosmic distances, exploring new worlds and unlocking the secrets of the universe. Wormholes, for now, remain a tantalizing mystery, a testament to the boundless possibilities of the cosmos. Section 8. Keep exploring the cosmos. Wormholes are a fascinating topic that blends science fiction and cutting-edge physics. They invite us to imagine a universe more connected than we ever thought possible. Want to learn more about wormholes, black holes, and the mysteries of the universe? Explore the resources available online and beyond. Keep asking questions, stay curious, and never stop exploring the wonders of the cosmos.